right, welcome back. We are now going to be looking at the graph of a derivative and analyzing it. There are times when you can find out the rate of change of something without knowing the position. Now, I think the best example might be driving in your car. Look at the speedometer. The speedometer tells you the rate of change of your car. It doesn't tell you where you are. So if we get a graph of rate of change, then what we want to do is we want to just sort of analyze that. And the first question that we're going to ask ourselves is, where is our function increasing? Well, our function is increasing when the derivative is positive. Here, our function is increasing. So I can immediately jump over to my chart, which of course we're making every time because why not, and say that in the intervals -4 to 2, I have a positive derivative. My function is increasing. At -2, my derivative becomes 0. From -2 to +1, my derivative is positive. It is equal to 0 at x equals 1, and it is negative in the interval from 1 to 4. So what do I now immediately know? Doing a little quick interpretation, I changed from positive to negative, which means that right here at x equals 1, there must be a local maximum on my function. Cool. Second question. Second question to ask myself is, when is it concave up? And I know that it's concave up when the second derivative is positive. So let's pick a different color. Second derivative is no, I wanted to pick a different color. Second derivative is positive. Well, second derivative is positive whenever the graph of the derivative is going up. So my second derivative is positive here, and my second derivative is positive here. So going back to my chart, I'll add second derivative, and on the intervals from -2 to 0, it is positive. In the interval from 3 to 4, it is positive. From 0 to 3, it is negative, and notice that it is 0 at x equals 0, it is 0 at x equals 3. See those horizontal tangents of the derivative graph? And it is 0 here, and it is negative there. Again, remember that this is the graph of the derivative. So we're not even looking at the function at this point. We're looking at the graph of what is the derivative doing, and we can figure out what the second derivative does. Now, does this mean I have any inflection points? Remember, inflection points, when the tangent exists, well, that's all three of those places, and the second derivative changes sign. So I have an inflection point here at -2 on the graph. I have an inflection point here at 0 on the graph. Got that staggered off just a little bit, but that is in fact at 0. I should do a better job of writing that. And I have an inflection point here at x equals 3. Again, the second derivative changes sign at 3 separate points. Each of those, by definition, is an inflection point. Now, the real question was, of course, however, where is it concave up? Concave up means an increasing slope, and therefore a positive second derivative, which means that my graph is concave up in these two intervals right here. Okay, local extrema. Well, I've already answered this question. Local extrema happen whenever the graph of the derivative changes sign. The derivative went from positive to negative, and we already determined that that was a local maximum, and that was right here. That's the only place the derivative itself actually changes sign. Over here, it's positive, and then becomes positive again. Over here, it's negative. Well, it doesn't even cross, so it's negative the whole time. All right. So what have we got now? We have three inflection points, a local maximum, and two situations where the graph is concave up, and we know that the graph is increasing here and here. Let's go ahead and see if we can make a sketch of this graph. So I'm going to put a set of axes right there. There's my y-axis at 0. I'm going to match up my x-axis. So what have I got? Well, there's a local max. And since the graph is increasing to the left and decreasing to the right, I know that my local maximum is actually an absolute maximum. Let's see, what have we got? We have an inflection point at 3. The graph is concave down all the way to 3, at which point it switches to concave up. There's my inflection point right there. I've got an inflection point at 0. The graph is concave down all the way to 0, at which point it switches to concave up. There's an inflection point. I've got an inflection point at -2, but notice, let's draw -2 in there. Notice that it is concave up until that point, and then it switches to concave down, but the graph always has a positive slope. It's increasing the whole way except where it becomes 0. So that is one possible graph. Now, we have no idea what our y scale is, but we know that there's an absolute maximum right here, that we've got 3 inflection points where it changes concavity, that the graph has a positive slope and is therefore increasing from here all the way to there and decreasing thereafter. That's probably a pretty reasonable estimate of what this graph looks like, and we found it based on only knowing what the derivative of this function was. So if you want to think of this in terms of a real life situation, you had somebody sit in your car and look over your shoulder and jot down velocities, speeds, as you drove down the highway. And you were then able to reconstruct a little graph of what might have been your position. All right, go ahead and do exercise 23 in the book. And we are going to end here and come back with a new video on motion on a line. So we'll be back. We'll see you then. Thanks for watching.